Hello to all you students at CMS College of Engineering and Technology. If you've got that applied chemistry exam on your mind, well, you are in exactly the right place. In this explainer, we're going to tackle Unit V on batteries, and we'll break down precisely what you need to know to absolutely ace this section. So here's our game plan. We're going to kick things off with the fundamentals. The basic rules that make all batteries tick. Then we'll do a deep dive into 3 specific types that will for sure be on your exam. The classic lead acid, the versatile nickel-cadmium, and of course, the game-changing lithium battery. We'll also take a look at fuel cells so you understand how they're different. And we'll wrap it all up with a cram sheet of the most important stuff to really lock in that good grade.
Okay, let's get into Section 1, Battery Fundamentals. Look, before we can even start comparing different batteries, we have to get the basics down cold. What is a battery, really? And what are those key terms you're going to need to know? Let's build that foundation right now.
So, when we talk about a battery, what do we really mean? It's better to think of it less like a single object and more like a team of little power plants. We call these electrochemical cells. Each one has its own anode and cathode, and by hooking them up in different ways, either in series or parallel, we can get the exact voltage and current we need for a device.
Inside every single battery, no matter the type, you'll find these 4 essential players. I like to think of it kind of like a racetrack. You've got the anode. That's the starting line, where electrons begin their journey. The cathode is the finish line, where those electrons end up. The electrolyte is like a special return path just for ions, which keeps the whole internal process going. And the separator? That's the wall down the middle of the track, making sure the anode and cathode never, ever touch. That would cause a short circuit, and that's bad news.
This is a great way to see how far we've come. The conventional era gave us the absolute workhorses, right? Like the lead-acid battery in your car. Right now, we're in the contemporary phase, which is all about making lithium-ion batteries hold more charge and juice up way faster. But the really exciting stuff is on the horizon. Emerging tech, like solid-state batteries. These promise a future with way safer and much, much more powerful energy storage.
Okay, pay attention because this is a must-know concept for the exam, the difference between primary and secondary batteries. Primary batteries are your use 'em once and toss 'em type, like the AAs in a TV remote. The chemical reaction that makes the power is a one-way street. It's totally irreversible. Secondary batteries, on the other hand, are rechargeable. Your phone battery is a perfect example. Their chemical reaction is reversible, so you can drain the power, then plug it in, and that forces the reaction to run backward, basically refueling it for the next time.
All right, time for our first deep dive, the lead-acid battery. This is the textbook example of a secondary or rechargeable battery. It is the heavy-duty workhorse that you will find starting the engine in pretty much every car, bus, and truck out on the road today.
So to really get how this battery works, you gotta know what's inside. The anode is made of spongy lead, and the cathode is lead dioxide. They're both swimming in the electrolyte, which is sulfuric acid. And really importantly, they're kept apart by separators. A typical car battery just strings 6 of these little 2-volt cells together in a series to give you the 12 volts you need to start the engine. So you turn the key and the battery starts discharging. What's actually going on in there? At both the anode and the cathode, the lead material reacts with the acid and gets converted into a totally new substance, lead sulfate. You can almost picture it as a white, crusty coating that starts forming on both plates. The key thing to remember for your exam is this. As the battery discharges, that lead sulfate builds up and the sulfuric acid in the electrolyte gets weaker and kind of watery. Now, recharging is just running that whole process in reverse. Once your car is running, the alternator kicks in and applies an external current. This forces that lead sulfate coating on the anode to turn back into pure lead, and the coating on the cathode turns back into lead dioxide. And as this happens, sulfuric acid gets released back into the electrolyte, making it strong again and getting the battery ready for the next start. So here are the big trade-offs for the lead-acid battery. On the plus side, it's cheap to make, it gives you that huge jolt of current you need to start an engine, and it works just fine in cold weather. But the downsides are pretty major. That lead is super toxic, which makes recycling a real environmental challenge. They're also incredibly heavy, and over time, they just lose their ability to hold a full charge. Okay, let's shift gears and look at 2 more modern types of rechargeable batteries. First up, we'll talk about the nickel-cadmium battery. You'll hear it called NiCd. Then we'll cover the lithium battery, which is the technology that has completely revolutionized our world of portable electronics. The NiCad battery uses a totally different chemical cocktail. The anode here is cadmium, the cathode is nickel oxyhydroxide, and the electrolyte is potassium hydroxide. See that double arrow in the reaction? That tells you the whole process is simple, clean, and totally reversible. And that reliability is what made it the absolute go-to choice for rechargeable gadgets for years and years. Everything from cordless drills to the very first cell phones.
So what's the big trade-off? Well, it's pretty clear when you lay it out like this. On one side, you've got some great advantages. NiCad batteries are smaller, they're lighter, and they last a lot longer than a lead-acid battery. But on the other side, there's the cost. They are way more expensive to produce. For portable devices, though, that extra cost was often worth it. And now we get to the lithium battery, truly a game changer. So what's its secret sauce? It's a solid-state battery. Instead of having a liquid electrolyte sloshing around inside, it uses a solid polymer. This brilliant innovation lets engineers make batteries that are incredibly thin, lightweight, and even flexible, all while packing a massive amount of energy into a tiny space. This is the technology that makes our modern world of smartphones, laptops, and electric vehicles even possible.
So far, we've only talked about batteries that store energy. But what if you had a device that never ran out of juice? What if, instead of recharging it, you could just refuel it? Well, that is the revolutionary idea behind the fuel cell.
This right here is the most important difference to lock in for your exam. A battery is like a storage tank. It holds a fixed amount of energy. A fuel cell, though, is more like a tiny power plant. It doesn't store energy, it generates it on the fly by consuming a fuel, like hydrogen. As long as you keep feeding it fuel, it'll keep making electricity.
Let's break down how the most common type, the hydrogen-oxygen fuel cell, actually works. As you can see, hydrogen gas, that's our fuel, is pumped into the anode. Oxygen, pulled right from the air, is supplied to the cathode. They react, and the only things that come out are electricity, some heat, and pure water. This process is so clean and so reliable, they actually used it on the space shuttle to generate both power and clean drinking water for the astronauts. Pretty cool, huh?
The big takeaway here is really a story of incredible promise versus some massive challenges. The promise? Super high efficiency, we're talking around 75%, and absolutely zero pollution. But the challenges are huge. The catalyst you need are often very expensive metals like platinum, and figuring out how to safely store explosive hydrogen gas on board a car is still a major engineering hurdle. Okay, deep breath. We have covered a lot of ground. So let's pull all those key concepts together onto one final cram sheet. If you've only got a few minutes to review before you walk into that exam, this is the slide you need to focus on.
Okay, let's do a final lightning round. Remember, primary versus secondary is just a one-way trip versus rechargeable. Lead acid is the heavy, high-current battery for cars. NiCad is the lighter, longer-lasting, but more expensive option. Lithium is the lightweight, high-energy density king for all our portable gadgets. And fuel cells, they aren't batteries. They're power generators that run on fuel. If you can explain the core parts, one key advantage, and one application for each of these, trust me, you are in great shape for the exam.
So, as you go into your exam, I want to leave you with this thought. The electrochemistry you're learning about right now isn't just for a grade. It is the fundamental science that is going to power our future, from the electric car in your driveway to the entire energy grid. Thank you for watching, and best of luck with your studies and on your exam.